Yeah, good evening, everyone. So, let us start today's session. If any of you find that somebody is waiting in the lobby, waiting to join, please do let me know so that I can let the person in. And is the screen visible to everybody?
Yes, it is visible.
Okay, thank you. So, mm, so good evening, everyone. I am Abhik Dev, and I am the teaching assistant for the course Thermodynamics me-65, uh, which is being taken by Professor Kale of IIT Delhi. So, mm I welcome all of you to the second live session of the course. Um, Today, we shall be discussing mostly on the um, concepts related to the first law of thermodynamics applied to closed systems and the concept of internal energy. So, most of these concepts were already discussed with you in the previous lecture of the course. So, these problems that we'll be solving today will be helping you to clear the mm, doubts that you might be having in this interrelated concepts. So, at any point, if you have any doubt, please do let me know. So, without any further delay, let us start today's session uh, with a numerical. This is a numerical related to the uh, mass flow rate and the mass balance in a system. So, a garden hose attached with a nozzle of diameter 2 centimeter is used to fill a bucket of capacity 50 liters. It takes 50 seconds to fill the bucket. Determine the mass flow rate through the nozzle and the average velocity through it. To take the density of water to be 1000 kg per meter cube. So, uh, a garden hose, like a pipe which has a nozzle attached to it, is used to fill a bucket, and that has a capacity of 50 liters, and it is said that it takes 50 seconds to fill the bucket. So we have to determine what is the mass flow rate from the nozzle that is required to fill the bucket of 50 liters in a time of 50 seconds, and what is the average velocity of the water that is coming out of the nozzle. So let us start. Uh, so what is the volume of the bucket? Volume of the bucket is 50 liters. Okay. So 1 liter is 10 to the power minus 3 meter cube. So we can convert it to meter cube in by multiplying it with 10 to the power minus 3 meter cube. Okay. So it is basically 0.05 meter cube. The bucket is filled in 50 seconds. So the bucket is filled in 50 seconds, which implies that a volume of this volume of water comes out of the hose or the nozzle in 50 seconds. Okay, so you can say that 0.05 meter cube is filled in 50 seconds. So what is the volume flow rate? Rate of water, this will be 0.05 by 50 as in meter cube per second. So this is 0.001 meter cube per second. So this is the volume flow rate of the water that is coming out from the nozzle. Okay, now what is the area of the nozzle? It has a diameter of 2 centimeter, therefore area of the nozzle is equal to pi by 4 diameter square. So 2 centimeter in meter, if we convert it, we can write it as 0.02 meter whole square. So this is pi into 10 to the power minus 4 meter square. Therefore, the mass flow rate through the nozzle the mass flow rate through the nozzle this will be equal to the volume flow rate. Let us denote it as volume flow rate. So the mass flow rate will be volume flow rate multiplied by the density. The density is given as 1000 kg per meter cube. So the mass flow rate comes out to be 0.001 multiplied by 1000. So it is 1 kg per meter cube. Sorry, it is 1 kg per second. And let's see here. So this is the nozzle. Okay. So from here, the total volume flow rate we know, and we know the area. So how can we determine what is the velocity? So essentially we can say that this area multiplied by the velocity of water at this point, the average velocity of water at this cross section. Okay, let us denote it as small v. Okay, so this area A multiplied by this average velocity at this cross section will give the volume flow rate. So this is AV. Therefore, the average velocity of water through the nozzle is this one. It is given as, let us denote it as A. So it will be V dot by A. Okay, so this will come out to be 0.001 by pi into 10 to the power minus 4. It comes out to be 3.18 meter per second. Okay, so this is the answer. So is it clear to everybody? This is a very simple problem of mass flow rate and continuity. So I hope it is clear to everybody. If there is any doubt, you can ask. Else we will move on to the next problem. Okay, so let us move on to the next problem. So in the previous problem, see, if the bucket has a hole, small hole at the bottom that leaks water at the rate of 0.2 kg per second, then determine the time required to fill the bucket. So now we have to perform a control volume analysis of the water in the bucket. So the bucket now has a, initially it was only, the water was only coming in. Now there is the water is also leaving the bucket through a small hole at the bottom. So we have to perform a control volume analysis of the water in the bucket at any point of time to determine how, at what rate the volume, the mass in the water is increasing. Okay, so this is the water is coming in, this is the water going out. So we consider that the water in the bucket at any time is the we consider the control volume to be enclosing the water in the bucket at any point of time. Okay, so how is the mass of the control volume changing? That is the mass of water changing with time. So dmcv, mass of water in the control volume with time. Okay, it is changing, it can be written as m in, it is the rate at which it is coming out minus the rate at which it is going out. Okay, so uh, it is the rate at which it is coming out is, we have found out from the previous problem, it is 1 kg per second. So 1 kg per second, and this is 0.2 kg per second. So the rate at which the net mass of water in the control volume is increasing, that is the mass of water in the control volume is increasing at the rate of 0.8 kg per second. Okay, so okay, so therefore uh, the mass of water in the control volume or bucket, you can write it as bucket only, because the control volume compasses only the mass of water. So in the bucket uh, rises at the rate of 0.8 kgs per second. Okay, so the volume that is filled in 1 second is 0.8 kg, and we divide it by, this is the mass, so mass divided by the density, that is 1000 kg per meter cube, will give the volume that is being filled per second. So it comes out to be 8 into 10 to the power minus 4 meter cube per second. And what is the, is there any doubt? Okay, okay, so but the, in liters, this is in meter cube, so in liters it will be uh, 1 meter cube is 1000 liters, so we can multiply it by 1000 and it will come out to be 0.8 liters per second. Okay, so the volume of the bucket is 50 liters, therefore 50 liters will be filled in 50 by 0.8, so this is 62.5 seconds. Okay, so you can see that because of the leak, the time that is required to fill the bucket has increased from 50 seconds to 12.5 seconds. So that is like this fraction, this is the 0.2 kg per second that is going out is accounting for the loss in mass, which finally increases the time required for filling the bucket. So I hope this is clear to everybody. So if it is clear, then we will move on to the next problem.
Yes, sir. It is clear, sir.
Okay, so let us move on to the next problem. So a rigid tank contains a hot fluid having an internal energy of 800 kilojoule. The fluid is stirred using a paddle that does 0.5 kilowatt of work on the fluid. The fluid loses 2.5 kilowatt of heat to the surroundings. What is the internal energy of the fluid after 200 seconds? Okay, so mm, uh, I hope that the first law of thermodynamics for a closed system is already clear to you from the lecture. So we will be making use of the first law of thermodynamics for a closed system in this problem, which essentially equates the heat transferred to a system and the work done by a system with the change in internal energy of a system. Okay. uh, Change in the total energy of a system, not the internal energy, essentially change in the total energy of the system. So here we are giving a rigid tank, okay, which contains a hot fluid that has an internal energy. Initially the internal energy is 800 kilojoule. Now the fluid is being stirred by a paddle, which does 0.5 kilowatt of work on the fluid, that is it does 0.5 kilojoule of work per second. Now the heat lost from the system is 2.5 kilowatt, that it is losing 2.5 kilojoule of heat per second. So if we neglect, see, this is a stationary system and we are considering that the height of this, the base height of this system from the datum is not very much, that is this the height of this system is not very much, so we can neglect the differences in the kinetic energy and the potential energy. Okay, so if we neglect the changes in the kinetic and potential energy, the change in the total energy will now equate to the change in the internal energy only. Okay, now from the first law of thermodynamics for a closed system, we can say that the change in the internal energy of a system is equal to, we are considering this to be the control volume, so or the system in this case, so this will be the Q, that is the heat transfer to the system minus the work done by the system. Okay, so what is the heat transferred to the system? It is losing heat. So from the sign convention of heat, we have found out that we are considering that the heat that is transferred to the system, that is heat transferred into the system, is positive, and the heat that is transferred out of the system, or heat that is being lost by a system, is taken as negative. So here the heat is being lost by a system, so the heat lost will be negative, and this is 2.5 kilowatt. So 2.5 into 10 to the power 3, and we multiply it by 200 to give the total amount of heat lost in 200 seconds, minus, so we know that the work, we by sign convention again, the work that is done by a system is taken as positive and work done into the system is taken as negative. Here the work is being done by the paddle into the system, so the work done is taken as negative here, so it is minus 0.5 into 10 to the power 3 into 200. Okay, so this value comes out to be, this is minus 500 and this is plus 100, so this is minus 400 kilojoule. Okay, so the, you can say that the change in the internal energy is given as this. So change is given as the final internal energy of the system minus the initial internal energy of the system is minus 400. Okay, so So what is the final internal energy? This implies that the final internal energy is the initial internal energy plus this value. So it will be 800 minus 400, that is 400 kilojoule. Okay, therefore the final internal energy after 200 seconds
हाँ बेटा
uh, is 400 kilojoule.
फिर घास वाले बाग में नहीं है कहीं भी नहीं है वो मिल गई वो थी वो आशी की मम्मी को टाइम लेंगे वो तो जस्ट अभी
I
अभी आई
think
है
some of any one of you has their mic on, so can you please turn it off? Yeah, thanks. Just let me know if this is clear, and then we can move on to the next part of the problem, which is basically will be a continuation or modification of this problem. So is this clear till now?
Yes, sir. Of course.
Okay, okay, so we will move on to the next part of the problem. uh, okay, just give me a minute. Okay, so see, in the previous problem, now we are replacing the starter, that the pedal work is replaced by an electric heater, which passes an electric current of 20 ampere through a resistance of 10 ohm. Now we have to find the rate of change of the internal energy of the system, and if it is and the next part of the problem is, if it is desired that the temperature of the fluid is to be kept constant at the initial value, what is the rate of heat loss required to achieve that? Okay, so first, so the pedal has been replaced by uh, a electric resistance heater. uh, uh, I think somebody has their mic on. Please, can you turn it off?
Yes, sir. Yes.
Yeah, sure.
So I just, yeah, so can I ask you one thing?
Yeah, do ask.
So can I ask you one thing?
Yeah, yeah,
Actually, I
sure.
lost the network in between, so I just want to. So can I see the answer of question number three for a minute or two? Because I
Yeah,
just lost
okay.
my network, so
Yeah,
I
yeah.
cannot go through. Just a minute, sir. I just
Okay,
so give me a minute. I just note it down so that I'll go through it later on. Just give me a minute. Huh?
okay,
Yeah, thank you.
okay. So, yeah, okay. So, yeah. So it is, yeah. Is there any doubt? Okay. So yeah, so the pedal has been replaced by an electric heater, and the internal energy was initially 800 kilojoule like the previous problem, and it is losing heat at the rate of 2.5 kilowatt. So electric work input. So what is the electric work input? The rate of electric work input. Let us denote it as W E dot. This is I square R. Okay. So 20 square into 10. that is 4000, that is 4000 watt or 4 kilowatt. So the 4 kilowatt is being input into the system now. Okay, so the heat loss, and the heat loss is as usual 2.5 kilowatt. So if we write the change in the energy, that is the energy balance for this control volume, we can write as usual, like the previous problem, we are neglecting the changes in the kinetic energy and potential energy. So the change in the total energy will be equal to the change in the internal energy only. So basically E will be written as U here. So the change in the internal energy of the control volume, okay, so this will be the rate at which heat is uh, coming into the system and the rate at which the work is done by the system, but heat is being lost here. So this is minus 2.5 kilowatt, and this is the work done on the system, so this will also be negative. So it will basically be 1 point plus 1.5 kilowatt. Okay, so from this we can say that this is the rate of change of internal energy of the system, and it is positive, which implies that the internal energy of the system will increase. So the relationship between the internal energy and the temperature is that the higher the internal energy of the system, the temperature of the system will be in most of the cases the temperature of the system will be higher. Okay, so as the internal energy of the system is increasing, the temperature of the system will also increase. Now what we have been asked for is if the temperature of the fluid is to be kept constant, then we are asked to determine the rate of heat loss required to achieve that. Okay, so increase in the internal energy implies increase in temperature. Okay, so to keep the temperature constant, what we have to do in essentially we have to keep the internal energy constant. To keep the temperature constant, fluid constant at initial value, the internal energy is to be kept constant. Okay, so that is U final will be equal to U initial, or delta U should be 0. This implies from the first law, the rate of heat input is equal minus the rate of work output should be equal to 0, or the rate of heat input should be equal to the rate of work output. The rate of work output here is 4 kilowatt. It is sorry, the rate of work input, this is the rate of work output from the system. So since it is the work is input into the system, so it will be essentially minus 4 kilowatt, and the minus sign, that is the heat equals to the heat transfer from the control volume now equals to minus 4 kilowatt. So the minus sign essentially indicates that the heat is to be lost, so negatives implies heat lost, heat loss. Okay, therefore the rate of heat loss to maintain the temperature constant is equal to 4 kilowatt. Okay, since we are already considering it as a heat loss, so we are not writing the negative sign here. So I hope it is clear to everybody.
Excuse me, sir.
Yes.
Sir, I think your connection was lost for 1 or 2 minutes, sir.
Okay, so which part
So,
did you miss? Can you just please tell me?
sir, whenever we have started that na, change in internal energy dcu by dt is
Hmm.
equal to 1.5 kilowatt, and after that, the things were not clear from your side.
Okay, okay. So
Uh,
am I is the video and the screen
yeah,
clear now?
screen is also not visible right now, so you please switch on your screen, I think, because it's your
Okay, okay,
face is
okay,
only visible.
okay, okay. Yeah, it can be. So please let me know if this happens. Okay.
Okay, definitely, sir.
Yeah. So so let me just go through it once again. So in this problem, we have found out that the rate of change in the internal energy is 1.5 kilowatt. That is, it is a positive quantity. So the internal energy of the system is increasing. Okay, but we have
Yes.
been asked to find out the rate of heat loss such that the temperature of the fluid will remain constant at its initial value. So what is the relationship between internal energy and the temperature of the system? So as the internal energy of the system is increasing, the temperature of the system also increases. So to keep the temperature of the fluid constant at the initial value, we have to keep essentially the internal energy constant. So the final internal energy has to be equal to the initial internal energy, or the change in the internal energy should be 0 to keep the temperature constant. So to keep the temperature constant, if we use the first law of thermodynamics, we can equate it to find out that the heat transferred to the system should be equal to the work done by the system. Okay, so this is essentially more like practically, if you think, the work is being done by this heater. So this heat, at the same rate that the work is coming in, or the heat the resistance heating effect is coming in, at the same rate, if the heat is being lost, then there will be no temperature change of the system. So this is essentially the same thing. So the heat loss should be equal to the work done by the system. So the work done by the system is positive, and since it is the work here, the work is done on the system, so it is minus we are taking, so minus 4 kilowatt, and the negative sign automatically implies that the heat is to be lost for the system to maintain its temperature. So the rate of heat loss to maintain the temperature is 4 kilowatt. So I think it is clear to everybody.
Yes, sir.
Yeah, okay. So then let us move on to the next problem. Like, uh, this is like quite an interesting one. So most of us have either been slapped by some person or have slapped somebody at some point of time, maybe. So we let us imagine a situation when one of us is being slapped by an angry person. So the temperature, so if the person is slapping on the face, then the temperature, we can feel some heating sensation on the face, right? So let us say that the temperature of the face is increasing by a value of 1.8 degrees Celsius, and this is, although it may not sound very significant, but if you feel it, this is quite significant to feel actually. So assuming that the slapping hand has a mass of 1.2 kg, and the face tissue that is being affected has a mass of 0.15 kg, we have been asked to determine what is the velocity of the hand that with which the person has slapped. So like so it can be taken as, if you are very angry on somebody, you can just do this calculation and determine, so with at what velocity you want to slap that person to make him feel a very high burning sensation. So anyway, this is kind of a practical problem, mm, and an interesting one also. So what happened is that, mm let us first understand what happens and why it rises. So the kinetic energy, so when you are slapping somebody, the kinetic energy at impact, the kinetic energy becomes 0. before impact it was having a kinetic energy, and on impact it becomes zero. So this kinetic energy that was initially with the hand, it gets converted, it gets transferred to the tissues, which results in the increase in the internal energy of the tissue, that finally increases the temperature. So the kinetic energy with which the hand strikes the face, we can just let me write it down. The kinetic energy with which the hand strikes the face appears as the increase in appears as the increase in internal energy and temperature okay of the face and hand. So if you slap somebody at a very high velocity, and even if not very high, I mean at a normal velocity only, you will feel that your hand is also, you are feeling that heat in the hand also. So not just the face, your hand will also be subjected to the result of the impact. So on impact with the face, we are assuming that the hand becomes stationary. Such that the final kinetic energy becomes zero. So since this kinetic energy, see, there is no heat transfer to the system. If we consider the at the impact, if we consider the hand and the face to be the system, the combined system, so there is no heat transfer to the system, there is no work done by the system, only the change, there is a change in the internal and there is a change in the total energy. There is no, I mean, not a change in the total energy, there is a change in the form of the total energy, that is the kinetic energy is being converted to the internal energy. So delta kinetic energy is equal to delta U. Okay, so like half into mass of the hand with which you are slapping into velocity square multiplied by, this is the mass of the tissue that is being affected, mc, c is the specific heat of the tissue, and delta t. Okay, so what is the velocity? This will be 2 into m tissue into c into delta t by mass of the hand. So if you put in the values, 2 into the tissue affected is 0.15 kg, the C is 1 kilojoule, that is 10 to the power 3 joule, and delta T is 1.8 degrees Celsius. So, and this is the mass of the hand is 1.2 kg. So this essentially comes out to be 21.21 meter per second. So it is the, as you can see, it is an quite a significant velocity that you need to slap someone with to have this rise in temperature. So it is not that easy also. So better why take so much of effort? So the velocity of the hand just before the impact is 21.21 meter per second. So I hope this is clear to everybody. Quite a simple one.
Excuse me, sir.
Yeah, please.
Sir, so in this case, if we want to consider
Yes.
the effect on the face, so our system will be only the that face, na?
No, we are considering, see, when you are impacting on the face, the tissue on both both the face and the hand will rise. So we can consider the palm of the hand and the face as a system.
Okay.
Okay, so the palm of the hand and the this thing just at the point of impact is taken as a system. So that is why it is being mentioned that 0.15 kg is the tissue, the combined mass of the face and the hand that is being affected. You cannot see, if you slap someone, the only not only the face will be having the effect, right? You cannot expect the hand to feel cold, right?
Yes,
So
definitely, sir.
the combined tissue, the combined internal energy of the palm of the hand and the face will increase. That is why we have to take both of these together as a system.
So in this case, sir, because this palm is coming from a distance,
Mhm.
so if we need to draw a system or the system boundary, so basically, what kind of the things we can expect, sir?
See, if you in this problem, if you want to have a system boundary, then you can
Mhm.
consider that this is the face and this is the uh, like this is the hand that is
Okay,
coming
okay.
in. So a
Yes,
combined this and the palm of the hand will be the system. So it is like a moving the boundary of the system will not be fixed; it will be moving. This is
yeah,
one case. And if we consider that we will consider the instant at which it is about to strike, then it will be like just about at the point of impact, so it will be like close to this one only. So you can
yes,
consider
yes.
the impacting interfaces of the two as a system.
Okay. So in this case, that work transfer, whatever it is there by the palm, so it will be, uh, that means how we can consider, because it is a same system, so there is no means work transfer at the boundary,
Yeah, so there is, see,
because hmm,
that is why we are considering the palm and the face as a system, because the work transfer, if we consider that you are lifting something, although you are not lifting something, okay, but if you consider
yeah,
that the mass of the hand is it is moving at a velocity, then you are moving it, resulting in some work, that is force,
hmm.
some displacement work you are considering, but in this case it won't be crossing the boundary.
Yes, yes, that's why I'm asking. So
So
basically, it is not crossing the
yeah,
boundary,
it
but
is not crossing
it
the
is
boundary.
within the system,
Yeah, it
basically.
is within the system. It is within the system,
Hmm.
and hence it will be considered as internal energy. That is not internal energy. The total, it will be a fraction of the energy of the system. That is the kinetic energy of the system. That it is within the system.
Yeah, because this thing is within the system.
Yeah,
Yeah.
because this thing is within the
Okay,
system.
okay. Fine,
Okay,
fine, sir. Okay,
okay.
okay.
So yeah. So then let us move on to the next problem. Okay. So just give me a minute. Okay. So a 50 kg of iron block at 80 degrees Celsius is dropped into an insulated tank that contains 0.5 meter cube of liquid water at 25 degrees Celsius. So determine the temperature when the thermal equilibrium is reached. The specific heat for iron and water are 0.45 kilojoule per kg degree Celsius and 4.18 kilojoule per kg degree Celsius. So this block of iron, 50 kg of iron, is dropped into a tank which contains water at 25 degrees Celsius. The temperature of iron is 80 degrees Celsius. This is initial condition. So what will happen now, since the iron is at a higher temperature and the water is at a lower temperature, so there will be a heat transfer between them, which will result in the temperature of the water to increase and the temperature of the iron to decrease. till the time when both of them will be approaching a same particular value of temperature, that is when the thermal equilibrium will be attained. Okay, so let us assume that the at thermal equilibrium point the temperature of water and the iron both becomes T, that is T degree Celsius. Okay, so what is the, we have to determine what is this temperature. So how will we do that? So any of you have any idea about how to proceed with this problem? Just a brief idea. It's a very simple one.
So maybe we can use the conservation of energy. We can start with the conservation of energy, like something.
Yes, conservation and of energy. So yeah, we will be using the conservation of energy. Essentially the this system, for this system the internal energy will be conserved, so we will be using a conservation of the internal energy here. So let us start. And why internal energy? Because the kinetic, and we are neglecting the changes in the kinetic and potential energies. Okay, so what is initially the internal energy? Initially the internal energy of iron. Okay, this is, let us denote it as UFE initially. So this is mass of the iron, the specific heat of the iron, and the temperature of the iron. This is the initial temperature of the iron, that is 80 degrees Celsius. And internal energy of water. Okay, so this will be U W initial, let us denote it as with the subscripts W and I. So this will be mass of the water, specific heat of water, the temperature of the water initially. Okay, now finally when the thermal equilibrium is attained, finally, okay, the internal energy of iron plus water in thermal equilibrium this is equal to, let us denote it as U final, that is will be MFE CFE, and temperature, now the temperature of iron will be T, plus mass of water, specific heat of water, and finally the temperature of water will also be T. Okay, so T is basically the equilibrium temperature. Let me write it, equilibrium temperature. Okay, so here the change in the kinetic energy is 0, the change in the potential energy is 0, there is no heat transferred to the system, there is no work done by the system. So what will the first law give? The change in the total energy will be equal to the change in the internal energy will be equal to 0. Okay, that is the initial internal energy of the system will be equal to the final internal energy of the system. So let us just write the values. Fe, this is for iron, this is for water, and finally MFE CFET plus MWCWT. So let us just simplify it. TFE minus T, and this will be MWCW T minus TW. Okay, so the mass of iron, it is given as 50 kg. The specific heat of iron is given as 0.45 kilojoule per kg. This is temperature of iron initially is 80 minus T. We are not converting it to Kelvin, essentially because we are taking it as a temperature difference, and T will also be something in degrees Celsius. So we are just concerned with the temperature difference. So even if we convert it to Kelvin, it will give the same value. And this is mass of water. So now mass of water, it is given that the tank contains 0.5 meter cube of liquid water. So the mass of water is equal to the volume of water multiplied by the density of water. So the volume of water is 0.5 meter cube and the density of water is 1000 kg per meter cube, right? So this is 500 kg. Okay, so this is 500 kg multiplied by 4.18, and this temperature will be T minus the temperature of water initially was at 25 degree. Okay, so this will be 80 minus T, and this is 92. If we simplify it, it will be something like this, T minus 25. So the temperature, final temperature will essentially come out to be 25.58 degrees Celsius, nearly equal to 25.6 degrees Celsius. So now you can see one interesting fact here, that the temperature of iron, 50 kg of iron, it is decreasing from 80 to nearly 25. I mean, it is having a drop of what, around 54 degrees, 54 degrees, whereas the temperature of water, okay, although the mass is significant, even if you do not consider it to be that high, that significant mass, the temperature of this water is increasing only by a fraction, like zero point 0.6. It is not even it is like 1 upon 80 times, 1 upon 80 times of what the temperature of iron is decreasing. This is essentially due to this specific heat. Okay, so what is the specific heat? It is basically the capacity of the of any material to store the heat. Okay, since water has a higher capacity to store the heat, so it will result in a, for so more heat will be required to increase its temperature, whereas since iron has a lesser capacity to store the heat, so comparatively lesser heat will be required to increase its temperature, or equivalently lesser heat is required to be removed for its temperature to drop. So this specific heat value, it is very, it is, I mean, throughout the your study as a engineer, this specific heat value will play a significant role in numerous aspects, not only in this just this energy balance. It will be very significant in the conduction, heat transfer, even, I mean, in other aspects of heat transfer that we'll be considering. I mean, when you do a course on heat transfer, it will be clearer to you. So I mean, just try to understand the significance of this parameter. Okay, so the equilibrium temperature is 25.6 degrees Celsius. Okay, so I hope it is clear to everybody. Let me know if there is any doubt in this.
Excuse me, sir.
Yes.
Sir, you just please show the previous slide just for few seconds.
Okay, just one.
Previous one, that just previous one.
Okay. Yeah.
Yes, sir. One is. Yeah. Thank you very much, sir. Thank you. Thank
Okay.
you, sir.
Okay. So I'm taking that there is no doubt in this. So we will now move on to the next problem. So uh, consider a 1000-watt iron. Okay, whose base plate. So most of us, we have been pressing our clothes using an iron since long, right? So this is also this kind of problem should also be quite like practical for all of us. So we are considering a 1000-watt iron whose base plate is made of a 0.5 centimeter thick aluminum alloy, whose density is 2700, not 2700, 2770 kg per meter cube, and the specific heat is 875 875 joule per kg degree Celsius. Now the base plate has a the base plate has a surface area of 0.03 meter square. Initially, the iron is in thermal equilibrium with the ambient air at 22 degrees Celsius. Now we are heating the iron using this. We are starting on the power supply. Okay, we are assuming that 85% of the heat generated in the resistance wire is transferred to the plate. Okay, why this 85%? So supposedly the iron is also a kind of resistance heating that we discussed earlier, like right, like this resistance heating. If you have ever opened up an iron and seen, so this is also a kind of a resistance heating. So what happens is that some of the heat that the resistance wire is generating, uh, uh, it can be such that this 100 watt, it a fraction of it might not be available for the iron base plate. How? It can be significant due to the it can be due to a significant number of reasons, like due to continuous waste usage. There can be a drop in the final heating effect of the resistance coil. Okay, so due to numerous effects, there it can be such that the final this 100 watt power is not being available for the iron plate. Okay, whatever be the reason, so 85% is being made available to the iron plate. Determine the minimum time needed for the plate temperature to reach 140 degrees Celsius. So you have said that at 140 degrees Celsius you will start to press the whatever cloth you are using, you are willing to press. So what will be the time required for the iron to heat up to that temperature? So basically this is also a significant practical problem, because most of the modern irons that are being designed, they are designed for a very wide variety of clothes. Okay, so you have to select the final temperature uh, to which this temperature, this final temperature with which you can press a cloth depends on the material of the cloth to material of the cloth. And so this, depending on this final temperature, this time required for the iron to be heated to that temperature will is also to be determined, and this determination depends on the this alloy that we are taking, and the surface area that will be made available, and also obviously the resistance heating component. So uh, like this is also kind of a practical problem that we do it in our practical life, but let us just solve a problem related to it, so that the next time we do it we can be clear. Okay, so this is what is happening. So in this case, see the volume of the iron plate that is available, volume of the aluminium base plate. Okay, volume of the aluminum base plate, V, let us denote, this will be this, it is, I mean, it has a surface area of 0.3 meter square and it is 0.5 centimeter thick. So what is the volume? So the volume will be is 0.03 meter square multiplied by 0.005, right? It is centimeter, so in meter it will be 0.005 meter cube. So this is the basically our system now. This volume of aluminum is the system now. So it is basically 15 into 10 to the power minus 5 meter cube. Okay, so what is the mass of aluminum that is being heated? Heated, this is this volume multiplied by the density. Okay, so this is basically 15 into 10 to the power minus 5 multiplied by 27 70. Okay, so this comes out to be 0.4155 kg. Okay, now if we apply the first law to the considering the aluminum base plate as a system, then Q is equal to the change in the internal energy. Again, we are neglecting the kinetic and potential energies, so the total energy equates to the internal energy plus this W. Okay, so there is no heat transferred to or from the system. Okay, we are not considering the heat losses here. Significantly, this has to be taken into an assumption that we are not considering the heat loss from the aluminum plate as it is being heated. Okay, if we take the heat loss, as a component, then this Q won't be 0, it will be some particular value as a negative value. And this W, so W is the electrical work input into the system by the resistance wire heating or this power supply. So this is W electrical, and this is minus 1000 is a watt into 0.85 into, this is the watt, this is 1000 watt, right? That is joule per second, that is, this is the energy supplied per second. Okay, so if we multiply it with the time of heating, we will get the total energy as the work input that is being supplied into the system. Okay, so okay, so the change in the internal energy will be equal to minus W, that is equal to minus of 1000 into 0.85 into T. Okay, so what is the change in the internal energy? This change in the internal energy will be the mass of this aluminum being heated, that is 0.4155. The specific heat of the aluminum being heated, that is 875, multiplied by the change in the temperature, delta T. Okay, this is this is minus, this another minus will come from here, so this will ultimately become plus 1000 into 0.85 into T. Okay, so this time, let us just use it to equate it, 0.4155 into 875 into the change in the temperature. So change in the temperature is 140 minus the initial temperature is 22 degrees Celsius. So, and this is 1000, 0.85. Okay, so this comes out to be 50.47 seconds. Okay, that is nearly, therefore the time required is equal to, nearly equal to, you can say 50.5 seconds. So you see, I mean, within such a small amount of time, the temperature is increasing from to about by around 80 degrees. Okay, so depending on this time, we can say how fast the iron will become heated to a particular temperature. So that is how we choose choose the setting of an iron. So I hope it is clear to everybody.
Excuse me, sir.
Yes,
So that means, sir, we are means making an assumption that base plate is there. So whatever the heat we are supplying,
yes,
so at within these 50 seconds, means no amount of energy is losing from the base plate.
yes, that is what I said, right? I mean,
Yeah.
we are assuming that the heat lost from the base plate, we are not assuming, we are assuming that no heat is being lost from the base plate at
Means
that point of
during
time.
this, yeah, during this 50.5 seconds,
Yeah,
means whatever the energy is supplying, but within this period, no energy is, means basically it is a kind of insulation we are means taking,
yeah,
means we are
you can
assuming.
say that. Yeah,
Okay, okay,
okay. Although
okay.
it is not practically the case,
Yeah, that's okay, okay. So,
but
but for
you can
yeah,
say that when you heat a iron,
Mm.
Okay, what happens is that there is no forced convection, right? How we are
Okay.
neglecting it, just let me tell you.
Yeah.
uh, it is in contact with air, right? And air has a very less thermal conductivity. I mean, its capacity to conduct the heat is very less. Okay, there is no forced convection. You are not turning on the fan while you are heating up an iron, right? So there is no forced convection, and the natural convection heat transfer coefficient, if you take, it will be around like 5 watt. Okay, or even in the range of that. And this is convection, so it is only by natural convection. And the rest part is radiation. So radiation comes significant only when the temperature is very very high, because we when if you I don't know if you have gone through the radiation heat transfer course or not. If you have gone through, you will be knowing that there is a term sigma in the radiation heat transfer, which equates to which has a factor 10 to the power minus 8. Okay, so only the temperatures which are very very significant, very very high, like in the orders of thousand. Okay, so that will have a significant temperature loss by radiation. So in that, so considering those aspects, the heat loss from the iron base plate will be not very significant in comparison to the heat that is coming in from the resistance wire heating.
Yeah, definitely. True, sir.
Yeah,
So that's why until and unless we start doing the ironing, means that means some cloth will come into the contact,
yeah,
and then due to that conduction, we can say
yeah.
whatever the
When you
energy
come,
will
so the
lose.
conduction is the when you start ironing, the conduction, it is again a solid body, right? So it will have a higher
Mm.
thermal conductivity. So
Yeah.
from that time onwards, you can say that this
It-
heat will be lost.
Okay. Heat is basically
Yeah. Okay.
okay. Very good. Sir, thank you very much, sir. Thank you very much.
Yeah. Okay. So now there is a question related to the internal energy of an ideal gas. So for this, some of the concepts, I mean, I am not some of the concepts which will be used in this problem, I will be discussing in the problem itself, so that it becomes clear to you. I think so that these concepts have already been discussed, but still let me just recapitulate so that it becomes easier. So from the first law of thermodynamics, we have this expression, that is q equals to delta u plus w, right? Where this w is work done by the system. Now this work done by the system can be of different categories. Like there can be a displacement work wherein the boundary of the system is being displaced, and that is the volume of the system is increasing or decreasing, that is it is changing against a particular pressure value, that is the displacement work. It can have a electrical work, it can have a surface tension work, it can have many other different forms of work. Okay, so uh, we broadly, let me write it as, this is a displacement work. This encompasses all the work that involves the displacement of the, or the movement of the system boundary, that is change in the volume against a particular pressure value. Okay, so this is the displacement work, and the all other forms of work. Okay, so let me write it as wo. So all other forms of work, electrical work, shaft work, then paddle work, or surface tension work, any kind of work, that all other forms of work are included in this. Okay, so this displacement work, okay, this can be written as integration of p dv. Okay, so this term, it is like the pressure that is causing the change in the volume. We are considering it at an infinitesimally small control volume. We are changing infinitesimally small change in the volume, that is dv, and the pressure that is causing that infinitesimally small change, and we are integrating it throughout the entire change in the volume. Okay, so uh, in this, I mean, writing the displacement work as integration pdv, if there is any doubt, you please ask. Okay, so I am taking that everybody, for everybody it is quite clear how we write the displacement work as integration pdv. So now for a constant pressure process, the pressure is constant, right? So it can be taken out of the integration. So integration p dv, it can be written as p integration dv, and so the integration of dv over the entire change in the volume can be written as p delta v. Okay, so this is the displacement work for a constant pressure process. Okay, now we define a term called enthalpy. Okay, we define this term as h, which will be sum of the internal energy plus the pressure of the system at any instant multiplied by the volume of the system at that instant. Okay, so at any instant, what is the enthalpy? Enthalpy is the sum of the internal energy at that instant plus the product of the pressure of the system at that instant multiplied by a product of the pressure of the system at that instant and the volume of the system at that instant. Okay, so we can write the change in the enthalpy as delta u plus P delta V plus V delta P. This is just operating this del operator on PV. So it is P delta V plus V delta P. Okay. So for a constant pressure process, if we are considering, then delta P is 0. Okay. And this P delta V plus delta U. Okay. So this change in enthalpy becomes, for a constant pressure process, it becomes P delta V. Okay, and so if we write this equation here, so q equals to delta u plus w can be written as w displacement plus other forms of work. So w displacement is P delta V, so it is P delta V plus other forms of work. Okay, so this delta u plus P delta V can be written as delta H plus the other forms of work, or if we take it this side, q minus other forms of work will is the change in the enthalpy. Okay, so this is for a constant pressure process. Okay, so is there any doubt in any of the steps that have been used till now? If there is any doubt, please ask.
Yes, clear, sir.
Okay, okay. Then let us move on to this next part. So now q is, again, let me write this expression, delta u plus w. Okay. Okay, so if we consider only displacement work here, so this can be written as delta u plus p into delta v. Okay, this is one expression. Now for a general expression u plus pv, from this general expression, when we write delta h is equal to delta u plus p into delta v plus v into delta p. Earlier we considered it to be a constant pressure process. Now we are writing it for a general process. For a general process, if we take it this side, then delta H minus V into delta P can be written as delta U plus P into delta V. Okay, so if we write it in this expression, if we put it in this expression, it becomes Q equals to delta U plus P into delta V, P into delta V. This equals to delta H minus V into delta P. Is there any doubt?
Excuse me, sir.
Yeah,
Sir, when we are writing on this slide, suppose Q is equal to delta U plus W.
yeah.
So here W is Only the displacement work we are talking about.
Yeah, we are, for the simplification of the expression, we have considered only displacement work. If we consider other forms of work, another term will come here.
Okay.
Okay, so just for a
Fine.
simplification of the expression that will be used here, to understand how the specific heat values are coming. Okay, for a simplification of that, we are using it. Only
Okay.
we are
Otherwise,
considering.
yeah. Otherwise, this W is basically consists of displacement work and as well as other work
Yeah,
also.
yeah, yeah. It is considered.
Mm.
It is considered to be for
Mm.
a displacement work as well as for other forms of work as well. Okay,
Okay.
but
Okay.
we are basically defining the specific heat values using the simplification that it is being defined for a, I mean, it is being formulated first for a system that is a simple compressible substance. Okay, for a simple compressible substance only, it will be P delta, I mean, the work will be only composing of the displacement work. Okay,
Okay. Okay. For simple compressible
compressible substances.
substances.
Yeah.
Okay. In that case, we are only going to take the displacement work.
Yeah, we are considering only the displacement work.
Okay. Okay. Okay, sir.
Okay, yeah.
Fine.
So this is delta H minus V delta P. Now if we consider it for a constant pressure process, sorry, for a, let us start with a constant volume process. For a constant volume process, okay, then Q equals to delta U plus P delta V, right? So this delta V for a constant volume process will be 0. Now how do we define the specific heat? The specific heat is defined as the amount of heat required to raise the temperature of unit mass of a substance by unit degrees. Okay, so that is the definition of specific heat. Okay, so what is the specific heat at a constant volume? Okay, so if so specific heat at constant volume is the amount of heat required to raise the temperature of a unit mass of a substance by unit degrees, provided the process of raising this temperature or supplying this heat is done at a constant volume. Okay, that is, the volume is kept constant. So this heat can be written as what? That is the mass of the substance, the specific heat at constant volume of the substance, and the rise in temperature. Okay, this is the mass of the substance. This is what is Cv. Cv is for unit mass and unit degrees. So when we multiply it with mass, the total mass and the total rise in the temperature, we will get what is the heat required for causing this change in temperature for this mass of the substance. Okay, and this equates to delta U. Okay, so we can write it as Cv, that is basically the change in the internal energy, can be written as m Cv delta T. Okay, that is or in terms of the specific internal energy, you can write it as Cv delta T, that is if we divide it by mass. Okay, so is it clear to till now?
Yes, sir.
Okay. Okay, so now for a constant pressure process. Q, now we will be writing the expression for delta H, delta H minus V into delta P. Okay, so this is, if for a constant pressure process, what will be the specific heat? It is the amount of heat required to raise the mass of raise the temperature of unit mass of a substance by unit degrees, provided the heat transfer is carried out at a constant pressure. So we used a subscript P here, Cp. Okay, delta T is, and this at a constant pressure process, this will be 0. So this is delta H. So we can write delta H as mCp delta T, or delta H is equal to m, sorry, this m won't come, this is a specific value, Cp delta T. Okay, so this value, this expression will actually be used in the problem. So uh, uh, that is why I thought that it is better to derive it first than directly jumping to it. So now let us go to the problem. So it is a piston cylinder device which initially contains a zero point 0.5 meter cube of nitrogen gas at 400 kilopascal and 27 degrees Celsius. Okay, an electric heater within the device is turned on and is allowed to pass a current of 2 ampere for 5 minutes from a 120 volt source. Now the nitrogen expands at a constant pressure and a heat loss of 2800 joule occurs during the process. Determine the final temperature of nitrogen. The specific heat of nitrogen at constant pressure is 1.039 kilojoule per kg. The constant pressure uh, heating is what we have derived, that is an expression for the enthalpy, and this will be used because of this context, because it expands at constant pressure. So what is the problem here? So this is a piston cylinder device, okay, and there is this piston. We are assuming the piston to be massless here. This is nitrogen gas which has a volume of 0.5 meter cube and 400 kilopascal and 27 degrees Celsius. So nitrogen is at this is having a volume of 0.5 meter cube, 400 kilopascal and 27 degrees Celsius. Okay, so now what the problem states: an electric heater within the device is turned on and is allowed to pass a current of 2 ampere for 5 minutes from a 120 volt source. So there is an electric heater here, okay, and this electric heater, it is 120 volt and it allows a current of 2 ampere to flow through it, okay, for a time of 5 minutes. Okay, it will result in an increase in the temperature of nitrogen. So this increase in temperature, or the this heating effect, it occurs at a constant pressure. I mean, due to this heating effect it will expand, right? Due to this heating effect, its temperature will rise and its temperature and pressure both will rise, and it will start to expand, and it will expand in such a way that at any point of time, the whatever due to this heating, whatever increase in pressure is happening will be compensated by the increase in the volume. So due to this increase in the volume, there will be a decrease in pressure, and due to this heating there will be an increase in pressure. So this will be, at any point of time, this will be balanced by each other, resulting in a constant pressure process throughout. So only the temperature and the volume of the nitrogen gas will increase. Okay, so it moves upward, and there during this process there is a heat loss of 2800 joule. So there is a heat loss of 2800 joule during the process. Okay, we have to determine what is the final temperature of nitrogen. Okay, so it will expand to a particular volume at that instant. After 5 minutes, what is the final temperature of nitrogen? Okay, so how will we go about this problem? So this is also essentially a conversion of this work and heat and into the internal energy, which will be causing the rise in the temperature. So this is just an application of the first law of thermodynamics. So Let us first begin by determining what is the mass of nitrogen here. So the mass of nitrogen in the piston cylinder device, that is PV by RT, where R is equal to, this is the universal gas constant by the molecular mass of nitrogen. So this is 8.314 by the molecular mass of nitrogen is 28, right? 28 gram per mole. So this will be 0.297 kilojoule per kg Kelvin. Okay. So, and what is the pressure? Pressure is 400 kilopascal, and the temperature is 27 degrees Celsius. That is, temperature is in Kelvin. It will be, here we have to write in Kelvin because the gas constant is having a unit of Kelvin. So let us convert it to Kelvin. So 27 degrees Celsius is 300 Kelvin. So pressure is 400. We are not writing kilo here because this kilojoule and kilopascal will get cancelled. I mean the 10 to the power 3 values will get cancelled. The volume of nitrogen is 0.5 meter cube. The R value is 0.297 and the temperature value is 300. So the mass of nitrogen comes out to be 2.244 kg. Okay. The heat lost, this is minus of 2800 joule, that is minus 2.8 kilojoule. And electrical work, now this is we are considering along with the electrical work, that this value, the work, other form of, in other form of work there will be electrical work. So the other form of work, that is the electrical work, this is equal to, see this will be the again the work done on the system, so it will be a minus that is a negative value, so minus V I T. Okay, so this is minus 120 volt multiplied by the current value, that is 2 ampere of current, 2 ampere of current is being passed, and the time is 5 minutes, right? So 5 into 60. So this is this value comes out to be minus 72,000 joule or minus 72 kilojoule. Okay, so if we put these values in this expression, okay, Q minus WO is equal to delta H. Q minus WO is equal to delta H, and this delta H is equal to we have found out that it equals to mCp delta T. So mCp delta T. Okay, so minus 2.8 minus of 72. Okay, this is equal to the mass of nitrogen, that is 2.244 into Cp. What is the Cp value? Is 1.039. 1.039 multiplied by the change in temperature, that is delta T. So this value delta T is equal to, this value comes out to be like what, minus 2.8 plus 72, that is 69.2, 69.2 divided by 2.244 multiplied by 1.039. Okay, so this value comes out to be 29.68. Okay, so the rise in temperature is 29.68 degrees. So the final temperature, is 27 degrees plus 29.68. Okay, so this value comes out to be 56.68, is nearly equal to 56.7 degrees Celsius. Okay, so this is the final temperature of nitrogen, mm, which due to this uh, resistance heating, under the effect of this resistance electric heater, and the heat loss. Okay, so is it clear to everybody how this has been solved? If there is any doubt, you can please ask.
Yes, sir. It is all right, sir.
Okay, okay then. Okay, then let us move on to the next problem. Okay, so yeah, so a piston cylinder device, it contains,
Uh, Excuse me, sir.
yes,
Sir, actual, sir, there is just I want to one concept from your side,
yes,
that in the previous problem it was the constant pressure problem basically.
yes.
So, sir, would you please just elaborate a little bit how it is basically the constant pressure, how it is remaining a constant pressure problem?
Okay, so as I have explained
Actu-
in
yeah, you
this,
have explained earlier. Yes,
yes, so what happens is that when you heat this one, its temperature and pressure are supposed to increase, right?
yes, of course.
Okay, so if this is a fixed surface, its temperature and pressure will keep on increasing because the volume cannot increase. Okay,
Yes,
but
definitely.
in this, due to this increase in pressure, suppose it was 400 kilopascal, now its pressure increases to 401 kilopascal. So initially this 400 kilopascal, it was balancing whatever outside pressure was being applied. So let us say the atmosphere itself was at 400 kilopascal. Okay, so under the influence, the force from both the side, this pressure 400 kilopascal and this atmospheric pressure 400 kilopascal, will be balancing the forces on this piston to keep it stationary, right?
Yes, sir.
Okay, so whenever there is an increase in the pressure on the bottom side, it will push it upward.
Yes,
So when it pushes, that the volume of this gas increases. So if we know the I mean the change in the volume, the pressure volume diagram for any substance, it looks like this. That is, as the volume increases, the pressure is supposed to decrease.
supposed to decrease.
Yeah,
Yes,
so
of
as
course.
this volume increases, okay, so as the volume increases, it will result in a decrease in the pressure. Say it decreases, this equivalent increase in the volume will cause a decrease in the pressure of like 1 kilopascal. So it will return back to, for any, at any small instant of time, although it is increasing, the due to this expansion, simultaneous expansion of the gas, it will the pressure will again simultaneously decrease, resulting in a constant pressure process. So,
So
so if it
that
is increasing to 401 kilopascal, due to this increase in 1 kilopascal, the amount 1 kilopascal pressure, it will result in a increase in the volume. This increase in the volume will cause a decrease in the pressure again, say minus 1 kilopascal. So this decrease in the pressure will keep this pressure constant at 400 kilopascal.
so that means, had this piston not been movable, so
Yeah.
in that case it won't possible.
No, in if the pressure is, if the piston, if it is not a movable boundary, it is never possible to maintain a constant pressure process, because in that case the volume is keeping constant, right?
Yes, volume
So,
is constant.
I mean, see, we know that from this equation, right? If you write it for an ideal gas, then this is PV equals to MRT. If volume is constant, mass is constant, right? R is also constant for a particular gas. So, if volume
Yes,
is constant, if the temperature with heating temperature is increased, then the pressure is bound to increase. There is no other way
also.
in which it will be constant.
Yes, yes. So only the thing is, whenever it is moving, the moving boundary is there, then it is means it is making in equilibrium conditions.
Yeah,
and
it is
having.
making, I mean, if we, it is a very, it is not in practical, it is practically, it is, it might not be such, but in
Mhm.
theoretical considerations, we consider that the piston is rising in such a slow rate that the increase in pressure is being compensated by the increase in the volume.
Increase in the volume, right, sir?
Yeah.
So it is practically, it is basically in this way we can explain the things. Okay,
Yeah,
fine.
exactly. That is how, basically, that is how you explain a quasi-static process. Okay, in which
Yeah,
supposedly if there are n number of weights placed on this one and you remove weights one by one, then it will start to expand. This will result in the decrease in the pressure. Okay, if we do not consider the heating part, if we remove the weights one by one, then the volume will gradually increase and the pressure will gradually decrease. Okay, so that is
yes,
how we explain a quasi-static process. So it is the same thing in this. Due to the temperature, there is an increase in the pressure which will result in at very small amount of time it will increase the volume by a very small amount, which will result in a equivalent decrease in the pressure and resulting in keeping the pressure constant.
okay. So that's why at that time we are taking the P delta V. That means
Yeah, that is how we
quasi
are taking
static.
P delta V. Yeah, that
Yeah,
is why.
that.
So the essential, so I asked you if there is any doubt in this. So essentially this expression, integration
Mm.
P delta V, can be written only for a quasi-static process.
Certainly, sir. So it is true for the quasi-static process in which we
Yes,
are keeping the pressure constant.
yes, pressure constant.
Fine, fine, sir.
Okay,
Okay, okay, sir. Thank you, sir.
okay. So let us move on to the next problem. So it is a piston cylinder device. It contains 0.05 meter cube of a gas initially at 200 kilopascal. At this state, a linear spring that has a spring constant of 150 kilonewton per meter, it is touching the piston, okay, but it is not exerting any force on it. It is just touching the piston. It is not exerting any force on it. Now, heat is being transferred to the gas, causing the piston to rise and compress the spring, okay, until the volume inside the cylinder doubles. Okay, so the doubt that you had in this problem, it will be further clarified in this, as we are using, we will now be solving a modification of this problem itself. Okay, so now in case of it being a free piston, we are considering that the piston is attached with a spring. So as the piston will move upward, it will cause the spring to compress and the resulting force will act downward. Okay, so it will I mean, as we go through this problem, the doubt that you had in the previous problem will be further clarified. So
Okay, sir.
hmm,
Fine, sir. Okay, okay,
so
sir.
causing the piston to rise and compress the spring until the volume inside the cylinder doubles. So if the cross sectional area of the piston is 0.25 meter square, determine the final pressure inside the cylinder, okay, and the total work done by the gas and the fraction of this work done against the spring to compress it. Okay, so just first let me write the draw the diagram of the system that we will be considering here. So this is the piston, okay. In contrast to the previous problem, here it is attached with a spring, okay, which has a spring constant of 150 kilonewton per meter. Okay, the volume of the gas is 0.05 meter cube and it is initially at a pressure of 200 kilopascal. Okay, this area of the piston is 0.25 meter square. So see, in the previous problem, this was a free piston. So the two forces on the two sides of the forces on the two sides of the piston were the atmospheric pressure or the ambient. Let us not consider atmospheric because atmospheric pressure is not 200 kilopascal. It won't be 200 kilopascal. So any ambient, the surrounding pressure that we are considering, the pressure of the surrounding is on this side and the pressure of the gas is this side. So at a balance between the two, you see that the piston is stationary. So in the previous problem, as the pressure was increasing, the piston could move freely upward because suppose this is 200 kilopascal, then in the balanced position initially, it would be 200 kilopascal at the surrounding also. So when the pressure increases to 201 kilopascal, there is this difference in pressure of 1 kilopascal on the two sides of the piston, that will result in the piston to move upward, and the pressure will then decrease in this the pressure of the piston, the pressure of the gas, sorry, pressure of the gas will equivalently decrease because this expansion of the gas. Now this is not such. What happens is that when, due to this increase in the pressure, as the uh, piston is trying to move upward, this spring is getting compressed. Okay, so from the relaxed position of the spring, as the spring is getting compressed, the when the see, this is a relaxed position, so when the spring is getting compressed, it will give an equivalent force in the downward direction. So as the piston is moving upward, the equivalent pressure on this side is increasing now. Okay, so to balance this, the pressure inside the gas, inside the cylinder, will also increase. Supposedly this is 200, the pressure increases to 210 kilopascal. The surrounding pressure remains at 200 kilopascal. Okay, so initially in the previous problem, what had happened, it had expanded till the time the volume had increased due to this pressure difference of 10 kilopascal. However, in this case, as it tries to expand, the spring will exert a downward force on this. Due to this downward force, the outside pressure, this force divided by this area, is also a pressure, right? So this equivalent downward pressure is also increasing, like 200 plus this value. So this will result, so to balance this increase in the pressure, due to this heating, the pressure of the gas also has to increase along with the increase in the volume. Okay, so this so as the volume is increasing, the pressure of the gas will also have to increase in this direction to maintain, to reach an equilibrium with the increasing outward pressure. So if there is any before going to solve the problem, you first if there is any doubt in this concept, please ask.
So, sir, now it is very much clear.
Okay.
So suppose in this case the pressure will be increasing definitely.
Mhm.
So for that we need to supply. We are supplying the heat or something else. Then only it will continuously going to increase.
Yes, yes, exactly. We are see, heat is transferred to the gas. This process will happen only if the heat is
Y-
being transferred to the gas. It won't
Yes,
happen automatically.
yeah, definitely. So that means that we are keeping the heat we are keeping continuously supplying the heat to this particular system. That
Yes.
means
Yeah, we are
okay,
supplying heat to the system. That is why the temperature of the system will increase. The pressure of
uh,
the system will also increase along with the volume of the system in this case.
yeah. So sir, now it is very clear. That means now the pressure is increasing, but at the same time there is means there it is not free to expand.
Yeah, it is
So
not free to
that's
expand.
yeah.
So
Okay.
since the downward pressure is increasing as well, so suppose the downward pressure increases to 250 kilopascal. So to balance it, it will come to a balance only when the pressure increases to 250 kilopascal, right?
Definitely, sir.
So that is why the pressure of the system will also increase.
Will also increase. And in the previous case, because there was no external agent
Yeah,
who is actually pressing it or
yeah.
something else,
So only due to
so
this
that's
temperature difference, there will be a free movement of the piston.
free movement of the system. So at every instant, it is maintaining the constant pressure
In the
in
previous
the
case.
previous problem. In the
Yeah,
previous problem.
yeah.
So it's very very good, sir. Very very clear, sir.
Okay.
Thank you. Thank you very much.
So let us start with solving the problem. So initial position of the piston is, so this is the initial position of the piston, right? We are taking this at when the volume is 0.05 meter cube. This is the initial position of the piston, and at that position the spring is relaxed. That is, there is no compression. Therefore, initial position of piston from bottom of the cylinder. Okay, this will be this initial volume by this area of the piston. Like this is the volume by area will give this distance. Okay, so this is sorry, volume of the piston is 0.05 and area of the piston is 0.25, so this is 0.2 meter. And final position of the piston from the bottom of the cylinder let us denote it as x1 and this is x2, this is v2 by area. So what is the final volume? It is said that the spring to compress until the volume inside the cylinder doubles, that is the final volume will be twice the initial volume. So this is 2.02 multiplied by 0.05, this is 0.25. Okay, so this is 0.4 meter. So what is the basically the displacement of the piston? So if the piston is rising from 0.2 meter to 0.4 meter, so it is displaced by a distance of 0.2 meter. So the spring equivalently gets compressed by a displacement of 0.2 meter. So displacement of the piston or that is equivalent to compression of the spring this is equal to x2 minus x1, that is 0.2 meters. Okay, so now we are assuming that the spring has a linear relationship with the displacement, that is the force that the spring will apply is a linear function of this displacement of the, that is compression of the spring. So considering a linear spring, the spring force acting is let us denote it as Fs. So this Fs, that will be K into delta x. Delta x is this, the compression of the spring. Okay, so this is 150 kilonewton per meter multiplied by delta x is 0.2 meter. So this is 3 into 10 to the power 4 Newton. So pressure due to this spring force PS 3 into 10 to the power 4 and it acts on the piston. So piston area is given as 0.25, so it is 120 into 10 to the power 3 Pascal or 120 kilopascal. Okay, so see, in absence of the spring, the concept that I have discussed, let me write it. In absence of the spring, the pressure inside remains constant at 200 kilopascal. Okay, but due to compression of the spring, the pressure inside increases linearly from 200 kilopascal to a final pressure of what will be the final pressure? Final pressure is the initial that when it was in imbalance with the surrounding, so 200 plus this increase in the pressure due to the spring force. So this is 120. So it will have a final pressure of 320 kilopascal. So from 200 kilopascal, in contrast to the free expansion of a free movement of the piston, in this case the pressure will increase from 200 kilopascal to 120 kilopascal to compensate the increase in the pressure force from the upward direction. Okay, so this is 320 kilopascal. Therefore, the final pressure inside the cylinder is 320 kilopascal. Okay, so what is the next part of the problem? The total work done by the gas. Okay, so this is part A. What is the total work done by the gas? See, we are considering a linear spring. Okay, that is the force is a linear function of the displacement. Okay, so since it is a linear spring, so the force due to it will also increase in a linear fashion due to the displacement. So the resulting pressure will also increase in a linear fashion. So from 200 kilopascal to 320 kilopascal, at 200 kilopascal the pressure was like this. The volume was 0.05 meter cube. Now the volume has doubled to 0.1 meter cube. Okay, so this pressure, it will also increase in a linear fashion like this, because we are considering a linear spring. So what is the work done? So if you focus on the work done value here, so it is an integration of the PDV value. This integration PDV value can be considered as the area under the pressure volume curve. Okay, so the area, essentially the area under the pressure volume curve gives the,
Excuse me, sir.
yes, yes, please go ahead. Please go ahead. Just a minute. I think there is some issue with the internet connection. Yeah, I think I had lost my internet connection. Uh,
Yes, sir. Sir, actually, no, since 2 minutes, I think your video was stuck off.
okay, so till where could you guys, I mean,
Yeah, it
see?
was, sir, that the 320 kilopascal when we got this answer, final pressure inside the cylinder. So
Okay,
after that, your video was stuck off.
okay. So let us continue from here. Okay, so since we are considering a linear spring, okay, so the force due to the spring will be a linear function of the displacement and hence a linear function of the volume. So the since force is since pressure is what the volume, so pressure force per unit area, so the pressure due to the spring will also increase in a linear fashion with the displacement and hence the volume. So, since we are considering a linear spring, that is linear variation of the spring force with the displacement, the pressure due to it will also increase in a linear fashion from 200 kilopascal to 320 kilopascal. Okay, as the volume increases from 0.05 meter cube to 0.1 meter cube. So if you focus on the value of the displacement work, we have written the displacement work as integration PdV. So this integration PdV is basically the work under the area under the pressure volume diagram. Okay, so the area under the pressure volume curve at any for any process will give the work done during that process. So the we are asked to find what is the total work done by the gas. So the total work will be the area under this uh, curve, this straight line. Okay, so what is the work done by the gas? The work done by the gas is equal to area under PV diagram. So this is basically a trapezoid, right? So you can write it, you can consider it as a trapezoid directly, or you can consider it as a this area of this rectangle plus the area of this triangle. So the area of this rectangle will be 200 multiplied by 0.1 minus 0.05. Okay, plus the area of the rectangle triangle is half multiplied by the base is again 0.05, and the height of the triangle is 120. Okay, so this kilojoule. Okay, so this will come out as 13 kilojoule. So 13 kilojoule is the total work done by the gas. Okay, now we are in the last part, we are asked to find what is the fraction of this work that is done against the spring to compress it. So see, if it was a free piston, okay, so how will the process be? From the previous problem you considered it, the pressure remains constant and the volume increases. So had it been a free piston, the movement of the process would have been like this. From 200 to, it would have been a constant pressure process, and the volume would have increased from 0.05 to 0.1. So this area, this rectangle area gives the work that is done against the surrounding, that is a surrounding which remains at a constant pressure of 200 kilopascal. And this increase in pressure, the work due to this, the increase in the pressure gives that is the area of this triangle gives the work done due to the increase in the pressure. That is, the area of this triangle gives the work done to compress the spring. Okay, so let me write it. The gas, in this case, the gas does work against the atmosphere at constant pressure atmosphere or the surrounding at constant pressure of 200 kilopascal, and against the spring at linearly increasing pressure increases from what? From 200 to 320, that is the pressure equivalently increases from 0 to 120 kilopascal. Okay, so the compression work on the spring that is equal to half multiplied by this area of this rectangle, area of this triangle only will give the compression work on the spring, that is 0.1 minus 0.05 multiplied by 120. So this gives 3 kilojoule. Okay, so this is the answer to the option question C. Now and alternatively we can also find the work done to compress the spring by the amount of energy that is stored in the spring due to this compression. So what is the energy, what is the expression for the energy that is stored in the spring? That is half k into the displacement square. So initially the spring is at
Half
rest.
kx square.
Yeah, half k
Displacement.
displacement square. Yeah, so half k per compression square. So initially it was there was no compression. So the delta x value that we found initially, that is the compression of the spring. So if we write it as the expression for the energy stored in the spring, then work done in compressing the spring, because the work done in compressing the spring will ultimately be stored as the spring energy, that is energy stored in the spring due to its compression. So compressing the spring, this is equal to half k multiplied by this 0.2 whole square. So if you put in the value of k is 150 kilonewton, so 150 into 0.2 square, so you will find out this also comes out to be 3 kilojoule. Okay, so this is essentially the same thing. Okay, so is this clear to everybody?
Yes, sir.
Okay, uh, so that will be all for today. So I hope I have been able to clear some of your doubts. So I will see you in the next class. And I am seeing that the people, the attendance of people is decreasing. I don't know why that is happening, but I hope that people keep on coming, because this live session uh, won't be fruitful if I mean the audience is very less.
Yes, sir. But it is really very much. I think it is a real gain, basically, what I am looking for, sir. So it is
Okay,
very fantastic session, sir.
thank you. And
Sir, yeah, definitely, sir. One thing I want to ask, sir,
yeah,
like we have submitted the assignments,
yeah.
so there will be some discussion on the assignment also after some time when they will be checked.
Essentially, the assignments are being checked by the TAs we are which who are at the host institute, right? This is a course of IIT Delhi.
Okay,
So
okay,
so the TA or the professor who is actually I mean who are offering this course will
okay.
actually be in charge of the assignments that you are submitting. The assignments that you are submitting won't be coming to us actually.
Oh, that's not a problem, sir.
Hmm.
But just the question is this: why we have submitted, and after that, I know that they will be evaluated, and we got the marks.
Hmm.
But those questions will be discussed by you or somebody else,
No,
sir.
actually, we are not supposed to discuss those questions.
Okay, 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 okay.
Okay, so
Hmm.
I mean, I hope that they have given a solution. They are uploading a solution of that also.
Maybe, sir, because in previous cases it was like that. They actually upload the solution,
Yeah,
but till now we did not receive. Might be afterwards they are
yeah,
going to.
might be afterwards. So, in any case, if there is any doubt with the solution, I suggest you to use the discussion forum of the course, so that the TA and the concerned professor they will also be able to help you out there.
Okay, certainly, sir.
Okay,
Certainly.
okay. Thank you. Thank you very much
Sure.
for joining, and I hope to see
Thank you.
you all
Thank you
in
very
the
much.
next class. Okay. Okay, then
Sure, sir.
you
Oh,
may leave.
sure.
Okay. Thank you.
Thank you, sir.
Thank you.